Math Humans. We're going to do 2.4 today. We're going to be talking about complex numbers. Our objectives are that we're going to review imaginary numbers, we're going to do math operations on complex numbers, and then we're going to manage complex conjugates. So first we should remember that the square root of a -1 is I, and then I know that I squared is a -1. So imaginary numbers are cool numbers. They're fun to make jokes about and have cartoons about, but we use them a lot in engineering and electrical engineering applications. And there's lots of uses for them, but those are two that I can think of right off the top of my head. So a complex number is going to be A plus BI. And if you'll remember, A is the real component and BI is the imaginary component, okay? The reason that they show up in this particular format, so if I want to graph a complex number, then this is the real axis and this is the imaginary axis, and a point would have coordinates real, comma, imaginary. So then that means that that point would have coordinates A plus BI. So we would write it in that form instead of our standard X comma Y format. So when you report a complex number, it always has to be written in this form. The real component has to come first because we would graph it that way. And then the imaginary component would come second because that would be the second part of graphing that particular function. All right, the math operations are very similar to math operations on other types of numbers. We tend to manage complex numbers as if they were variables. And what I mean by that is like things play together. So if I have A plus BI, and then I'm going to add C plus DI, the real pieces play together and the imaginary pieces play together. So this would be A plus C, and then the next part would be BI plus DI. So just like with variables, like things play together. All right, so then if I have A plus BI and I subtract C plus DI, again, like things play together, so this is A, bad math, minus C, and then I'm going to do BI minus DI because I have to distribute the negative. The next one is, what if I have A plus BI and I multiply it by C plus DI? And this kind of creates a special situation. So if I do, however you choose to do, this is A times C plus A DI, and then plus C BI, and then plus B DI squared. But remember that I squared is a -1, so I would write this as AC, and then this is going to change this term to be a minus BD, so minus BD, and then plus ADI plus CBI, and then we'd be done. So the only thing that you really have to be careful with when you're doing things with complex numbers is to pay attention to an I squared, because an I squared is a -1 that changes the sign of the term. So let's start by doing some examples. So this is going to be example 1, and the directions say, do math, my absolute favorite. So I'm going to have 4 plus 7i, and then plus, and this is going to be the A piece, 1 minus 6i, like things play together. So then this is going to be 4 plus 1, and then I'm going to have a 7i minus 6i, so this is 5 plus 1i. The B part is going to be 4 times a -2 plus 3i, and so this is going to be a -8 plus 12i. That one was easy. The C part is going to be 2 minus I times 4 plus 3i. I'm going to put this in a box just because I think it's a very nice way to organize math. It's not really necessary, but I'll show you what happens when we do. So I wrote my two things. Here's my little crappy box. So I have 8, 6i, minus 4i, and minus 3i squared. That guy's going to change. Remember, I squared is a negative 1. A negative and a negative, this is going to be a positive. My like pieces are on my diagonals. So this is going to equal 8 plus 3 is 11. 6 minus 4 is 2i. I just think the box is polite because it helps you to not miss terms, and it makes that organization a little bit easier. All right, the next concept that we want to talk about are complex conjugates. And they are very helpful when we are trying to eliminate problem terms. So if I have 3 plus 2i, the complex conjugate is 3 minus 2i. The first term always stays the same. The second term is going to be the opposite sign. And let me show you what happens when you multiply complex conjugates together. So if I have 3 plus 2i, and I multiply by 3 minus 2i, I'm going to get 9, and then I'm going to get a negative 6i plus 6i minus 4i squared. The I squared makes a negative 1, so this is a positive 4. These two terms cancel. 9 plus 4 is 13. So multiplying by a conjugate gets rid of the potentially problem situation. Okay? So let's do another one. Let's say I had a negative 7 minus 3i. The complex conjugate would be a negative 7 plus 3i. Okay? And let me show you again what happens if I multiply those two together. Alrighty, and actually I'm going to take a shortcut because if you'll notice, this is a difference of two squares. And in a difference of two squares, the middle terms always cancel. So on this one, I'm just going to do a negative 7 and a negative 7 is a positive 49. And a negative 3 and a positive 3 is a minus 9i squared. So this is 49 plus 9, which is going to be 58. So conjugates or complex conjugates are actually kind of cool. Here's a radical conjugate. That sounds like it's going to be such a problem child. So a radical conjugate, I spelled that guy wrong. So let's say I had 1 plus radical 3. Well, the radical conjugate would be 1 minus radical 3. And the same thing would happen if I multiplied those two together. I'd get 1 minus radical 3 plus radical 3 minus 3, because a radical 3 times a radical 3 is 3. The middle terms cancel. 1 minus 3 is a negative 2. So conjugates are really cool because they eliminate some difficult math. So now we're going to take that and apply it to complex fractions. So let's say I have a complex fraction and it looks like a plus bi over c plus di. This is the problem. We can't leave complex numbers in the denominator, so we would have to multiply by c minus di over c minus di. Okay? In the numerator, I'm not going to multiply the numerator out. I'm just going to leave it like this, for example, c minus di. But in the denominator, by multiplying by the conjugate, we created a difference of two squares. So this would end up being c minus d squared I squared. And so this would be c, bad math, c squared plus d squared. And now there would be no i's in the denominator. So now let's do an example with one of our complex fractions. So this is going to be our second example. And I'm going to have 2 plus 3i divided by 4 minus 2i. And my favorite directions, do math. Okay? I don't have to worry about the numerator. I can have complex numbers in the numerator. I just am not allowed to have complex numbers in the denominator. So I'm going to multiply. I'm going to take my 2 plus 3i over 4 minus 2i, and I'm going to multiply by the conjugate of the denominator, 4 plus 2i. In the numerator, I'm going to get 8, and then plus 4i plus 12i plus 6i squared. This is going to change to be a negative 6. And then in the denominator, I'm going to have 16 minus 4i squared. And again, I'm not going to show that I multiplied it out because in a difference of two squares, the middle terms always cancel. So 4 times 4 is 16 minus 4i squared. This becomes a positive 4. Now I'm going to combine like terms. 8 minus 6 is going to be 2. 4 plus 12 is plus 16i over 16 plus 4 is 20. Now remember when we talked about complex numbers, they have to be in the form a plus bi. That means then that I have to split this fraction up into two pieces. So this is going to be 2 over 20 plus 16i over 20. This is 1 over 10 plus 4i over 5. And then that would be my solution. Alrighty, and then if you reported it well, you would say 2 plus 3i over 4 minus 2i is going to equal 1 over 10 plus 4i over 5. Alrighty, so that was pretty nice. So now let's do an example just because we can with a radical conjugate. So the third example is going to say do math. Woohoo! And I'm going to have 3 over 1 minus radical 2. So I need to manage the denominator. So I'm going to multiply by the radical conjugate, 1 plus radical 2 over 1 plus radical 2. So this is 3 plus 3 radical 2 over, and again, it's a difference of two squares, so it's 1 minus a radical 2 times a radical 2 is 2. So this is 3 plus 3 radical 2 over a negative 1. And so we would write 3 over 1 minus radical 2 is equal to, I typically bring the negative to the top, 3 minus 3 radical 2. And then we're all done. So that was actually pretty simple. All right, so now we need to go to the logical conclusion. Why is this in this particular chapter? Let's talk about solutions to quadratics. So in theory, if I have y is equal to ax squared plus bx plus c, because it's a second degree polynomial, I have two solutions. But there are times when those solutions can look a little bit different. So if my parabola crossed the x-axis twice, then I would have two real solutions. Okay? If, on the other hand, my parabola bounced off of the x-axis, I would have one real solution with a multiplicity of 2. Okay? And then if I had a quadratic that was floating in space, I would have two complex solutions. And I could find those two complex solutions a variety of different ways. All right. I want to do a problem now with radicals because many of you haven't done radicals in a while. So let's do another example. In this one, I'm going to have the square root of a negative 48 minus the square root of a negative 27. We treat radicals as if they are a variable, and the insides, or whatever's under the house, have to look the same before you can manage the radicals. So 48, and I'm going to show you how I reduce radicals. It's my own, that's not my own method. I didn't develop it, but it's called a factor T. Factor T. I don't like tree diagrams, these guys, because I think numbers get lost. But in a factor T, numbers tend to be really easily managed. On the left-hand side are prime numbers, and on the right-hand side is the quotient. All right, so I'm going to start by doing 3 goes into 48 16 times, 2 goes into 16, 8, 2 goes into 8, 4, 2 goes into 4, 2, 2 goes into 2, 1. When you do a factor t, you always have to have a 1 in the bottom right-hand side. Remember when I reduce a radical, numbers come out in pairs? So a negative 48, so this is the square root of 48i, because remember the square root of a negative is I. This is going to be 2 times 2 radical 3i, which is 4 radical 3i. So we just managed the 48. 27 is pretty easy, but we'll do it this way just in case. 3 goes into 27, 9. 3 goes into 9, 3. 3 goes into 3, 1. I have a set of 3's that come out, so this is minus 3 radical 3i. Okay, so if I write this here, now these guys can play together. So 4 minus 3, notice that the radical 3's are the same. If they're not the same, you can't do the math. 4 minus 3 would be 1 radical 3i, and that would be my solution. Okay? Alrighty. And then I think we're done with that particular problem. So let's do another example. Example 5 says solve, and then I have x squared plus 4 is equal to 0. That's pretty easy. This is a plus, so I'm going to take it to the other side. Negative 4, x is going to equal plus or minus the square root of a negative 4, which is plus or minus 2. That's the square root of 4, and then there's the I. So then x is equal to plus or minus 2i. Well, that was pretty easy. Alrighty, I have 1 or 2 more examples. I can't quite remember. So for example 6, it says do math. Woohoo! We love math. If I have 2i over 2 plus I, plus 5 over 2 minus I. So this is a tricky situation because I have 2 complex fractions, so I'm going to manage each fraction separately. So in the first fraction, 2 plus I, I'm going to multiply by its conjugate, 2 minus, 2 minus I. And the second one, 2 minus I, I'm going to multiply by its conjugate, 2 plus I. Okay? Now I can do this math. So 2 times 2 is 4i minus 2i. And then in the denominator, this is going to be 4 minus I squared, which is plus 1. Alrighty, and then that denominator is going to be a 5, plus 10 plus 5i. And oh look, I'm going to have the same denominator, 5. Well, that worked out pretty politely. So now 4i minus 2i, just checking my math, except that should be 2i squared. So this is going to be plus 2, because an I squared is a negative 1. So now I can just simplify. So I have 2 plus 10, that's a 10, plus 4i plus 5i over 5. So I'm going to get 12 plus 9i over 5. Remember, I have to split it up so that I can report. So this is 12 over 5 plus 9i over 5. And then I would write 2i over 2 plus I plus 5 over 2 minus I is equal to 12 fifths plus 9i over 5. And then that one's all done. So that was actually pretty simple. Alrighty. And lucky dogs, that turned out to be your last example. Yeehaw!